In this video, we will be talking about partial pressures, and we will introduce the concept of what we will call a mole fraction. Up to this point, when we've been talking about gases and like the ideal gas law, we've been talking primarily about a one-component mixture. We're now going to expand that idea to talk about more realistic gases, ones that have multiple different components mixed into them. So mixtures of gases and the term partial pressure. So most of the gases that you're going to be working with are not going to be pure gases. Even if you buy a gas cylinder that is labeled as maybe oxygen, there's still going to be trace components of other gases in there. Very rarely will you ever work with a pure gas. So dry air, for example, is a mixture of nitrogen, oxygen, argon, carbon dioxide, and a bunch of other trace gases. The primary component of that is nitrogen. Nitrogen makes up roughly 78% of the air. The next is oxygen, which is 21%, and then argon, which is about 0.9%. Carbon dioxide currently is about 0.04%, and then there's a bunch of trace gases that make up the remaining 0.06%. So in certain applications, you can think of the mixtures as though they were one gas. Mathematically, the ideal gas equation, PV equals nRT, still works when you're working with mixtures of gases. If you heat up a mixture of a gas, it will, in terms of the pressure and volume, it will still behave the same way as if we were looking at a single component gas. So even though air is a mixture and its pressure, volume, and temperature, we can treat them as though it is one substance. By knowing the air's pressure, volume, and temperature, we can actually calculate the total number of molecules in an air sample, even though they are comprised of different compounds. Now, it was Dalton back in the late 1700s, early 1800s, who was investigating gases and came up with what we now call the law of partial pressures. So according to the kinetic molecular theory, which we were using previously when we described the ideal gas equation, according to the kinetic molecular theory, the particles themselves have negligible size and they are not going to interact, right? So there is no attractive force between the various components in the gas phase, and the size is negligible. The vast majority of the space in a gas is empty space. The molecules that are moving around make up a tiny fraction of that space. So the particles themselves, although they have different masses, they all have the same kinetic energy at a particular temperature, right? So the temperature itself, as we had talked about in one of the previous videos, is really a way of measuring the kinetic energy or the average kinetic energy of the gases. And we had said at that point that heavier gases, they will move slower, but they still have the same amount of kinetic energy. And when we're measuring pressure, the pressure itself is measured based on the collisions. So when let's say laser pointer here is a molecule, when it collides with the side of our container and changes direction, it's changing momentum. And that change in momentum is done by the force of the container wall acting on the molecule. So that force per unit area is what we measure as pressure. So regardless of what the gas is, because it has the same kinetic energy, the change in the momentum when it hits the wall is going to be the same. So what Dalton proposed is that the total pressure of a gas mixture is the sum of the partial pressures, or the amount of the force being exerted on the wall by each one of the component gases. So if you have like dry air, where 78% of the components are nitrogen gas and 21 are oxygen, though nitrogen gas and oxygen gas are very similar in mass for an individual atom, they will be moving at slightly different speeds, right? They'll have the same kinetic energy if they're in the same container and have the same average temperature. So both of them will be colliding with the side, but they'll be colliding at a different velocity, but they'll be hitting it with the same amount of kinetic energy. So because 78% of the molecules that are hitting the side are going to be nitrogen and 21% roughly are going to be oxygen, the total pressure is a sum of the pressures that's coming from the nitrogen and the pressure or the collisions on the wall that are coming from the oxygen, as well as the argon and carbon dioxide and all the other subcomponents. Now we can take our concept of the total pressure being equal to the sum of the individual pressures and come up with something that we were going to call the mole fraction. So if we take our equation, P total is equal to PA plus PB plus PC plus whatever other pressures we have, we can rewrite each one of our pressures using our ideal gas equation, where our ideal gas was PV equals nRT. If we rearrange this to solve for P, we would divide both sides by V to move the V to the other side. This cancels out V on the left-hand side, and so we get P is equal to nRT over V. So if we take our equation, the pressure total, and replace each one of the pressures with our ideal gas equation written such that pressure is by itself, so the pressure of A would be equal to the number of moles of A times RT. Because everything is in the same container, the temperature is going to be the same. R is a constant, so that will be the same. Also, because everything is in the same container, the volume will be the same. So we don't have a volume for gas A. We don't have a temperature for gas A. They're all in the same container, so they all have the same volume. Because we're talking about temperature as a measure of the kinetic energy, and after they collide, they're going to be distributing their energy amongst themselves, the temperature will be the same for each one of our gas components. So we will add this plus the number of moles of B times RT over V plus the number of moles of component C times RT over V, and we can keep doing this for how many ever different components we have. Now you'll notice that we have this repeating term, RT over V, in each one of these, so we can pull that out, rewrite this as our pressure total is equal to the number of moles of A plus the number of moles of B plus the number of moles of C plus whatever other gas components we have, that quantity times RT over V. So this sum here, what's within the set of parentheses, these values, we're essentially adding all the moles together. So this component here is the total number of moles. So our pressure total, because it's comprised of the pressures or the force exerted on the side of the container of each one of our subcomponents, that is equal to the total number of moles times RT over V. Now we have this idea, and we're going to call it the mole fraction. So our mole fraction, if we look over in this area, our mole fraction is equal, we're going to be using the symbol chi A for the A component. This is equal to the number of moles of the component we're interested in divided by the total number of moles. Okay, so if we were to take our mole fraction and replace the N with an equation that has pressure in it, So we're going to take our PV equals nRT. Solving for n, right, we would divide both sides by RT. On the right-hand side, our RT is going to cancel out, giving us PV over RT is equal to n. If we now use the same concept that we had before of our partial pressures, what we can do is come up with another way of determining the partial pressure given the total pressure based on this idea of mole fraction. So if we work in our space over here, right? So taking our concept of our mole fraction, and we're going to replace our number of moles with our equation that we have here. So instead of NA, that would be the pressure from component A times the volume over RT. Again, the volume and the temperature are going to be the same because they're in the same container. The partial pressure is going to differ because that's a measure of the individual molecules colliding with the side. So that top part is essentially our N sub A. When we're looking at our mole fraction, the bottom part is N total. And we had worked out right here, right, that P total is N total times RT. So if we rearrange it the same way that we did here, we can take our initial equation here, which is the N sub A, divide that by what we would have for the total number of molecules in the gas phase, essentially taking our bottom equation here and rearranging it to solve for N, we would get P total times V over RT, right? That bottom part is the same thing as N total. We can now cross out some terms. Essentially we have R, 1 over R divided by 1 over R. The R's cancel out. The volume over volume here, those cancel out. The T over T, those cancel out. And so we're left with a similar value for chi, where chi, our mole fraction of whatever the A component is equal to the pressure of A divided by the pressure total. We can rearrange this to solve for the pressure of A, and we get the partial pressure of our A component is equal to the mole fraction of the A component times the total pressure of the gas. So what this is saying is that the pressure that comes from our A component is equal to the fraction of the moles that are the A component out of the total number of moles times our total pressure, right? So our chi A here is the number of moles of A divided by the number of moles total. So this is essentially kind of like the percent of our molecules, atoms or molecules, in the gas phase compared to the total number. If we multiply that by our total pressure, we can find our partial pressure. And this concept, our Dalton's equation for partial pressure, is going to be something that we can use to do useful stuff later. So this equation here is the useful one that we will be using later to solve a bunch of stuff. Now, an example of where we might see partial pressures used in maybe not everyday life, but in a real world example, is deep sea diving. So in a previous video, we had talked about how Boyle's law, which relates pressure to volume, is used for divers. And as you go down further in depths of water, the pressure being exerted onto your body from the water increases by roughly 1 atmosphere for every 10 meters that you go down. The way that you're still able to breathe at those depths is that the regulator, the thing that you're breathing through, adjusts the pressure of the air to a higher pressure to counteract the water pressure pushing in on you, which enables you to expand and contract your lungs. Now, because of the hemoglobin in your blood and Henry's law, which we will talk about in chapter 13, the higher the pressure, the more oxygen that will dissolve in your blood. So typically our bodies are perfectly happy breathing in regular air, which is 0.21 atmospheres. So at 0.21 atmospheres, that's regular surface concentrations, our body's able to handle it. The oxygen is perfectly fine. If you were to go mountain climbing, where the pressure decreases, the partial pressure, or the percent of oxygen in the air is the same, but the partial pressure goes down. So by Henry's law, which relates gas pressure to how much gas gets dissolved in liquid, as the pressure goes down, the amount that's dissolved in the liquid goes down. So the amount that would dissolve in your blood goes down as the pressure goes down. So people who are hiking mountains will often run into a problem of what we call hypoxia. That is a low blood oxygen concentration. They're still breathing in air that is 21% oxygen, but because the pressure of the gas that you're breathing in decreases as you go up, the partial pressure of the oxygen is going down. So it's still 21%, but at elevation, it's no longer 0.21 atmospheres of pressure. So you can get to a point where maybe the atmospheric pressure is half an atmosphere, which would mean that the partial pressure of oxygen would be half of what it is down at sea level. So you'd be looking at about 0.1 atmospheres of pressure. That is when you start running into issues of hypoxia, which is why a lot of mountain climbers bring pure oxygen with them to inhale, to actually allow them to have a blood oxygen concentration that is back into the safe region. At atmospheric pressure, or pressure that's down at sea level, roughly 1 atmosphere of pressure or 1 bar, you can actually breathe in pure oxygen. It won't cause problems. You'll be sort of here in your blood oxygen content. But if you breathe in oxygen at higher pressures, it can cause problems. So let's say we're talking back about our scuba diver who's going down maybe 30 meters. You're going to be breathing in air at 4 atmospheres of pressure. The oxygen is still going to be 21%, but if you're inhaling 4 atmospheres of pressure, 21% of that is 0.84 atmospheres. So that would put you right about here. That's still perfectly safe. Now, there are deep sea diving that occurs where people are working on like oil platforms out in the ocean where they are far deeper than 30 meters. In some cases, they're actually working at several hundred atmospheres of pressure. Now, if you're working at even 20 atmospheres of pressure and 21% of that is oxygen, you'll run into a situation where you're actually inhaling about 4 atmospheres of pressure of oxygen, which would put you into a situation where you actually have too much oxygen dissolved in your blood. This can actually be toxic. So what deep sea divers do is they actually breathe in air that has less than 21% oxygen in it. It's actually called HELOX, which we'll see in the next problem that we're going to be working on. It's actually a mixture of helium and oxygen, where the concentration of the oxygen is actually fairly low compared to what we would be breathing in on the surface. So let's take a look at that particular problem. So let's say you have a scuba diving tank that contains this HELOC gas, a helium-oxygen mixture, right, of 24.2 grams of helium and 4.32 grams of oxygen, and you're filling it at room temperature, so 298 Kelvin. We want to calculate, so before we go down, scuba diving very deep, we want to know what we're actually breathing in and are we going to be safe. So we'd want to know the mole fraction and partial pressure of each one of the components to make sure that as we get fairly down deep in the ocean, we're not going to be breathing in too high of a partial pressure of oxygen at depth. So first thing we need to do is figure out how we're going to be doing some of these calculations. So first thing we're going to look at is we're going to calculate our mole fraction. So when we calculate our mole fraction, the mole fraction again is represented with chi. Chi of a particular component, as we had just talked about, is equal to the number of moles of component A divided by the number of moles total. Okay, so let's calculate, find our mole fractions for each one of the components. So what we need to do is figure out the number of moles of our helium. We will figure out the number of moles of helium. We'll figure out the number of moles of oxygen. And then we'll be able to, because the gas is a mixture of helium and oxygen, we'll be able to figure out our total number of moles, and then we'll just use for A either helium or oxygen depending on which one we are calculating. Right, so let's start by figuring out the number of moles of helium. Right, so the number of moles of helium is equal to our 24.2 grams of helium times, we're going to use our molecular weight with moles on top, grams on bottom. 1 mole is 4.0026 grams. Our grams are going to cancel out, leaving us with moles of helium. If we plug this into the calculator, you'll get 6.04607 moles of helium. In terms of significant figures, we have 3 significant figures with our mass. We have more than that with our molecular weight. And so our end answer, if this is where we were stopping, would cut between the 4 and the 6. But because we're going to be using this for subsequent calculations, we want to keep a couple extra digits so that we don't introduce a rounding error. Okay, next we're going to calculate the number of moles of oxygen. So we're going to use the same similar method, 4.32 grams of oxygen. Multiply that by the molecular weight of oxygen using moles on top, grams on bottom. 1 mole is 31.9988 grams. Our grams cancel out, leaving us with moles of oxygen. Plug this into your calculator, you'll get 0.135005 moles of O2. Again, we're going to have 3 significant figures because our mass has 3, our molecular weight has more than that. Okay, so now we're actually ready to calculate our mole fractions. So our mole fraction, let's do mole fraction of oxygen first. So that's equal to the number of moles of oxygen divided by the total number of moles, which would be the number of moles of helium plus the number of moles of oxygen, right, as our denominator. So this would be equal to 0.135. We're going to keep a couple extra digits so we don't introduce a rounding error. Moles of O2 divided by, we will mark where our sig figs are, divided by our number of moles of helium, which is 6.04607 moles plus 0.135005 moles. Around here, around there. Close our parentheses. Okay, plug that into your calculator. You get 0.021841168. This one doesn't have a unit on it because our units of moles over moles will cancel each other out. So our mole fraction doesn't have units, but this is the number that we would have. Our top has 3 significant figures. Our bottom will also have 3 significant figures. And so our number would cut between the 8 and the 4. Okay, now the mole fraction for helium, that is going to be the number of moles of helium divided by number of moles of helium plus oxygen. That will be equal to 6.04607 moles divided by the same thing we did when we were looking at oxygen. So 6.04607 moles plus 0.135005 moles. Make sure you wrap your denominator set of parentheses, marking our sig figs. Okay, this gives us 0.978158332. Our values, because it is a fraction, should actually add up to be 1. Right? It's kind of like a percent, although we're not multiplying it by 100 to convert it into percentages. So in terms of significant figures, our top value has 3, our bottom value will also have 3, so this will cut between the 8 and the 1. Now, those are actually our first two. We're trying to find the mole fraction, so our answer would be, this one for the mole fraction for helium, this for the mole fraction for oxygen, cut and rounded to the correct number of significant figures. The next part we want to do is find our partial pressures. So we can use our ideal gas equation to find the pressure for oxygen. So the pressure for oxygen is equal to the number of moles of oxygen times RT over V. So we'll have this being equal to 0.135005 moles times R, which is 8.314 Pascal meter cubed per mole Kelvin. Okay, our moles are going to cancel out. We'll now multiply this by our temperature. We're filling the tank at 298 Kelvin. Our Kelvin will cancel out. We have a 12.5 liter tank. So to get rid of the meters, we need to put that on bottom, right? As well as our equation here says put the volume on the bottom. So 1 divided by, and we're just going to convert it straight into decimeters, 12.5 cubic decimeters. We can multiply that by 10 decimeters per 1 meter cubed. And that will get us, we'll go up here, our pressure for the O2 would be equal to 26758.78 pascals, which is 0.268 bar. Okay, we can actually do the same process for helium, right, where we would replace, essentially the only thing we need to do is replace this value here with our number of moles for helium. So that would be our 6.04607, right, moles. All the rest of the numbers stay the same because it's in the same container, so it's at the same temperature. It's in the same container, so it's at the same volume. R is a constant, so it doesn't change. So we can calculate our pressure for helium, right, using the same general format. And what we'll find is that the pressure for helium is 1198.365 Pascal, which when we're all done, because our values, each one of our values here has 3 significant figures, right? Our end answer will only have 3 significant figures. So that's why we have 0.268 bar for our pressure of oxygen, right? That is our answer for our partial pressure for oxygen. Our partial pressure for helium would be 12.9 bar. And 1 bar is pretty close to 1 atmosphere of pressure. They're within 1% of each other, right? And so these would be our partial pressures here, and these values here would be our mole fractions. The total pressure would be the sum of our two partial pressures. And so that would end up giving us, when we add these two together, we would get 12.3 would be our end answer for our total pressure. Right, so this would be all of our values. Okay, now the way that gas is typically collected, at least in a simple laboratory setting, is you have some sort of a method for producing the gas. And in this case here, the way that we're producing the gas is we're going to be producing hydrogen gas by having zinc metal react with hydrochloric acid. That ends up producing hydrogen gas. The hydrogen gas is coming through the tube, bubbling down, going through this tube, and bubbling out into a glass container. When you start out doing one of these methods, the water is all the way to the top. And as the gas, the hydrogen gas bubbles up, it pushes the water out. And so what that leaves is mostly hydrogen gas. However, some of the water will actually evaporate. So you're going to have some water in the gas phase above the surface of your water. Okay, so gas itself is often going to be collected by displacing water from the container. That's what we were talking about. The problem with this is that because water itself is going to evaporate, you're going to have some water vapor in the gas phase. In some instances, if water isn't going to be a problem, that's not an issue. In other conditions, there are some substances that are very reactive and will react violently with water. And so you need to be aware that if you're producing a gas sample this way and water is going to be a problem, that you have to come up with a way of removing water. There are certain compounds that will pull water from a gas sample, like magnesium sulfate will do it. And so you would need to make sure that you're running your gas sample back through maybe some magnesium sulfate or something else to remove the water vapor from your gas. Now, because this is a mixture of the gas you're interested in, hydrogen, plus something that, if you're not interested in, could be considered a contaminant, we're dealing with another situation where we have a partial pressure. So the partial pressure of the water vapor is called the vapor pressure. So we can actually figure out how much water is going to be up in the gas phase, and it's temperature dependent. So the vapor pressure depends only on the temperature, right? It doesn't matter whether we're trapping hydrogen gas, oxygen gas, helium gas, it doesn't matter. The partial pressure of the water that's going to be above the surface of the water is going to be a constant value. And that value, the partial pressure, is called the vapor pressure. Now, the way that we will typically find this is look it up in a table, and that's how you can tell how much is going to be in the gas phase. So, vapor pressure for water, these are the typical pressures that you can expect. In millimeters of mercury, we can do a simple conversion to bar or atmosphere. 1 atmosphere is 760 torr, 1 torr is 1 millimeter of mercury, and then 1.01325 bar is 1 atmosphere. So we can actually go between them depending on what particular unit of pressure we want to use. The key part here is that you can see that even at roughly freezing, you still are going to have some water vapor sitting above your surface. So if you're collecting your gas sample, you're going to have some water in it, and that can cause problems. So let's now finish looking at another example of how we can use our ideal gas equation to solve problems. So let's say you have a volume of hydrogen gas, or we're trying to determine the volume of hydrogen gas. So what volume in liters of hydrogen gas at a particular temperature, 355 Kelvin, and a pressure of 738 millimeters of mercury, do we need to synthesize 35.7 grams of methanol? So this could be an example of where you're mixing some gases together and you're trying to produce a gas that you're interested in, right? So gas reactions. So our game plan is going to be, what we currently have is we know the grams of methanol that we want. So we can go from grams of methanol what we're ultimately interested in is hydrogen. So anytime we're given one substance, in this case our methanol, and we want information about something else, our hydrogen, we're going to need to get our first component into moles so we can use the mole-to-mole ratio that we find in a balanced chemical equation. So our first plan should be change from grams of methanol to moles of methanol. And then for moles of methanol, we can use our balanced chemical equation to go to moles of hydrogen. And then because we have moles and we want volume, we're going to use our ideal gas equation to go from moles to volume. Right, so we'll use this to go to moles of hydrogen. So let's work this out. So we're starting out with 35.7 grams of methanol. So that's CH3OH. Multiply this, we want to get rid of grams, so we're going to put grams on bottom. Moles go on top. 1 mole is, our molecular weight is 32.04216 grams of our methanol. Our grams of methanol cancel out. So we're now in moles of methanol. So we have successfully made that first transition. We're now in moles of methanol. We want moles of hydrogen. So we're going to multiply this by our mole fraction that we get from our balanced chemical equation. So that would be moles. We want to cancel out moles of methanol, CH3OH, and we want to convert into moles of hydrogen. The values that go into our fraction come from our balanced chemical equation. So our value for methanol, because there's nothing here, that's a 1. 1 goes there. And then for our hydrogen, our coefficient is a 2, so 2 goes on top. Our moles cancel out, leaving us with moles of hydrogen, which is our second transition that we were interested in. Now we want to go from moles to volume of our hydrogen gas. Okay, so perhaps the easiest way to do this is to align our R value to get rid of the moles. So we want to get rid of moles. Our R value is 8.314 Pascal meter cubed per mole Kelvin. Okay, our moles will cancel out. We can see that we have something that will give us liters eventually. This is meters cubed. Meters cubed is a volume, and so that works well for us. You know, that's telling us we're going in the right direction. It's on top, which is where we want it to be. We can get rid of our temperature, our Kelvin units, by multiplying by 355 Kelvin. Our Kelvin unit cancels out, and now we just have pascals that we need to get rid of. The unit that we were given is in millimeters of mercury. So we're going to divide by our pressure. We want the 738 millimeters of mercury on bottom. And now we're going to continue this calculation. sort of ran out of room, we'll continue it over here. Okay, pascals and millimeters of mercury don't cancel out, but what we can do is use a conversion. So we want to get rid of millimeters of mercury and convert into Pascal so that we can get everything to cancel out. So 760 millimeters of mercury is 1 atmosphere. So 760 is 1 atmosphere, and 101,325 Pascal is also 1 atmosphere, which means that our ratio of 760 millimeters of mercury is the same as 101,325 Pascal. Our millimeters of mercury will cancel out, and our pascals will cancel out, leaving us with the meters cubed. We want our answer to be in liters, and so we'll need to convert our meters cubed into liters. Keeping in mind that a cubic decimeter is a liter, so we're going to convert into decimeters. We're going to convert out of meters, which is the unit that we currently have. So 1 meter is 10 decimeters. We want to cube that because we have meters cubed. Our meters cubed now cancels out. And then 1 liter is a cubic decimeter. Our cubic decimeters cancel out. So we now have the liter, which is the unit that we were after. Right? It's a little bit of a lengthy, bit of dimensional analysis, but as long as you keep track of your units, you'll end up with the correct answer. Plugging in this into your calculator, you'll get 66.8858 liters. In terms of significant figures, our first value has 3. Our molecular weight here has a lot more than 3. Our mole fraction, these are whole numbers, so they don't come into play. Our R value has 4, so we're still left with 3. Our pressure that we were given has 3. This one here is a definition conversion, so is that one. So that means that we will have a total of 3 significant figures when we're all done. So the volume of hydrogen as our answer would be 66.9 liters. That would be our end answer.